Dear students, in today's class, we'll discuss a numerical method named modified Euler's method to solve linear differential equation of first order and first degree. Let's first discuss the iteration method and then we'll discuss few problems on this. We are going to apply numerical method to solve a linear differential equation of first order. So for this, let's consider a linear differential equation where the initial conditions are given to us. So the differential equation we have considered is dy by dx is equal to f of x comma y, and the initial condition given is y of 0 is y naught. We need to calculate y at x1. x1 is x naught plus h, where h is the step size. For this, we'll first use Euler's formula to get the initial approximation. Euler's formula is given by y1 of 0 is equal to y naught plus h times f of x naught comma y naught. This value will act as an initial approximation for the solution. Since the accuracy of this formula, this result, is not good, we are going to use modified Euler's formula. Modified Euler's formula is an iterative formula to get the solution of desired accuracy. For this, we'll be using the formula for y1 of 1, which is given by y1 of 1 is equal to y naught plus h by 2 times f of x naught comma y naught plus f of x1 comma y1 of 0. Remember what was x1? x1 is x naught plus h, and y1 of 0 we have got it from the Euler's formula. This particular iterative formula can be used multiple number of times to get the desired accuracy. If we have to calculate y1 of 1, what will be our value? y1 of 2, y1 of 1 we have got. Now if I have to calculate the next iteration, it will be y1 of 2. We denote it by second iteration by y1 of 2, and the formula will be y naught plus h by 2 times f of x naught comma y naught plus f of x1 comma y1 of 1. You remember the change is only from y1 of 0, now we are using y1 of 1. So similarly, we can write the formula for y1 of 3. This process we need to continue till we get successive values of y same up to 4 decimal place. Okay, let's see now a problem and to solve a differential equation using modified Euler's method. So the problem says, using Euler's predictor corrector method. Remember, modified Euler's method is also known as Euler's predictor corrector formula. So the problem says, using Euler's predictor corrector formula, compute y of 1.1 correct to 5 decimal place. And they have given dy by dx plus y by x is equal to 1 by x square. And y is equal to 1 at x is equal to 1. And And they have asked us to find the analytical solution also. Okay, so let's start. First, we need to write the problem in the standard form, means dy by dx is equal to. So we get dy by dx is equal to shifting y by x on the other side. It will be 1 by x square minus y by x. And if we take LCM and simplify, we get dy by dx is equal to 1 minus x by x square. Okay, so dy by dx is our f of x comma y. So we get f of x comma y is equal to 1 minus xy by x square. The initial values of x naught and y naught given in the problem are 1 comma 1. So x naught is 1 and y naught is also 1. Remember, we need to find the value of y at 1.1 and the initial value of y is 1. So the difference between the y value and y naught value will be our h. 1.1 minus 1 will give us h. Okay, if h is not mentioned in the problem, we use this method. Now let's calculate first f of x naught comma y naught. So f of x comma y x naught comma y naught, by replacing x by 1 and y by 1, we get 1 minus 1 by 1, which will be 0. Here in this problem, x1, the formula for x1 is x naught plus h, and that will be 1.1. We need to calculate y at 1.1. Okay, so it means we need to find y of x1, which is y1, and that is nothing but the value of y at x is equal to 1.1. So first we'll employ the Euler's formula to get the initial approximation value. So Euler's formula, we have y1 of 0 is equal to y naught plus h times f of x naught comma y naught. Okay, so if we substitute the initial values, we get y naught of 0 means the initial approximation as 1. So this value will be getting it is 1 because f of x naught comma y naught is 0. The second entire term will become 0. We get only y naught and the value of y naught is 1. Okay. Now we use the modified Euler's formula to get the iterative values of desired accuracy. So to start with, the first value will be y1 of 1. The formula is y naught plus y naught plus h by 2 times f of x naught comma y naught plus f of x1 comma y1 of 0. Okay, so let's substitute the values, replacing x by x1. So plugging y naught is 1, h is 0.1, so 0.1 by 2, f of x naught comma y naught we have got 0, f of x1 comma y1 we replace x and y by x1 and y1 in the expression for f of x comma y. So substituting the values, we get y1 of 1 is equal to 0.9959. Okay, so now we'll use the second iteration, y1 of 2. So y1 of 2 will give us 1 plus 0.05 times. We are using the same formula. We are just replacing y1. Earlier y1 of 0 we got 1. So this value now will be replaced by y1 of 1, which is 0.9959. So Simplifying this expression, we get y1 of 2 is equal to 0.99605. Okay, so we'll use the iteration formula one more time. Now y1 of 3, y1 of 3 will be 1.05. Again, you can see in the expression only the y1 value is getting changed. So y1 of 2 we are replacing here. Now 0.99605, what we have got earlier still, and simplifying we get this. You can see the last two values of y's are exactly same. So we can stop the iteration here, and the desired value of y of 1.1 will be 0.99605. Okay. In the problem, they have also asked us the analytical solution. Though it is not the part of the sum, but it is a quick revision of what we have learned in the previous semester. So quickly, I'll discuss the analytical solution with you. So if you look at the differential equation, you can make out that it is of the form dy by dx plus py plus is equal to q. So we're aware that this is a linear differential equation. To solve linear differential equation, we first uh, use the solution of linear differential equation, which is y times e to the power integral of dx is equal to integral of q times e to the power integral dx dx plus c. Substituting the value of p. So first we'll find out the integral e to the power integral p dx. So p here is 1 by x. So we get e to the power log x, and e to the power log x is nothing but log x. Substituting this in the formula, we get this yx is equal to integral of 1 by x square times x. So x square and 1x will get cancelled. So integrating, to simplify, we get integration of 1 by x is equal to log x. Okay, now we use the initial condition. The initial condition given as y of 1 is equal to 1. So we get the value of c, log 1 plus c is equal to 1. Log 1 value is 0. We get c is equal to 1. So the final answer, the final solution for the given differential equation will be y is equal to log x plus 1 divided by x. Okay. So to verify the answer what we have got is correct or not, in this expression we will substitute the value of x as 1.1 to check the value of y at 1.1, and you'll see that it is same as what we got the solution numerically. Okay, so now let's see another problem. Another problem says, using modified Euler's method, find y at x is equal to 0.2, given dy by dx is equal to 3x plus half of y, with y of 0 is 1, taking h is equal to 0.1, and they have specified in the problem that perform 3 iterations in each step. So what does y of 0 is equal to 1 indicates? Y of 0, 1 indicates that x naught value is 0 and y naught value is 1. Okay, we need to find y by taking h is equal to 0.1. So it is a two-stage problem, two-step problem. So first, let's start with stage 1. In stage 1, we'll write down whatever data is given to us. So if you observe, your x naught value is 0, y naught is 1, h we have zero point 0.1, and f of x comma y is nothing but dy by dx, which is given as 3x plus y by 2. Okay. Now from this, we will find out the value of y of f of x naught comma y naught. So f of x naught comma y naught, we get it as zero point 0.5, replacing x by 0 and y by 1 in f of x comma y, we get zero point 0.5. Now what is x1? x1 is x naught plus h. x naught they have given us 0, h value is zero point 0.1. So from first stage, we get the value for y of x1, means y of 0 0.1. Okay. So for this, let's start. First, we need to use the Eulars formula to get the initial approximation. So Euler's formula is given by y1 of 0 is equal to y naught plus h times f of x naught comma y naught. Substituting the values of y naught, h and f of x comma y naught, we get y1 of 0 as 1.05. Okay, now y of 1.05, y1 of 0 is equal to 1.05 is the initial approximation. To get the solution of desired accuracy, we need to employ modified Euler's formula. Okay, so we'll apply the modified Euler's method. The first iteration will give us y1 of 1, which is y naught plus h by 2 times f of x naught comma y naught plus f of x1 comma y1 of 0. Substituting the values, y1 of 0, we can take it from the previous step. So we get y1 of 1 is equal to 1 plus 0.05 times 0.8 plus 1.05 by 2. So when you feed this in the calculator, you get the value for y1 of 1 is equal to 1.06625. Remember, this is a simplified form of the modified Euler's formula for this particular problem. To get y1 of 2, we need to just replace 1.05 by 1.06625, what we have got earlier. You can see here y1 of 2, entire formula is same, 1 plus 0.05, 0.8 plus this value 1.00625. We have got it from previous step, divided by. Okay, so in the next iteration, if we want to calculate, you just need to replace this numerator by 1.0667. So if we apply the third iteration, the result we get is y1 of 3 is equal to 1.0667. You can see both the values of y of the last two iterations are same. So we can conclude that y1, y of 0.1 is 1.0667. Remember, but the problem is to find the value of y of 0.2, y of 0.2. So now we need to go to the stage 2. In stage 2, our x naught will be the x1 of the previous stage. The x naught will be 0.1, y naught is the y1 of the previous stage. So y1, whatever final answer we have got, 1.067, that will be our y0. Okay. We'll calculate f of x comma y will remain same as the previous stage. The function dy by dx value will not change. So f of x comma y is 3x plus y by 2. We'll calculate what is f of x naught comma y naught by replacing x by zero point 0.1 and y by 1.667. So we get f of x naught comma y naught as 0.8335. Okay, now we'll find out x1, which is x naught plus h, and x naught, remember, it's zero point 0.1 for stage 2, so zero point 0.1, and h value is also zero point 0.1, so it will be 0.2. So in stage 2, we get the value of y at x is equal to 0.2. So let's start. We'll first apply the Euler's formula. So formula will remain same, y naught plus h times f of x naught comma y naught. Substituting the value of y naught, h, and f of x naught comma y naught, we get y1 of 0 is equal to 1.15. Okay, so this will be our initial approximation. So to start the iteration, we'll be now using the modified Euler's formula. Modified Euler's formula will give us the value for y1 of 1, the first iteration result. So it will be f of this 0.8335. 0.8335 is nothing but f of x naught comma y naught, and 3x1 plus y1 of 0 by 2. This is our f of x naught, x1 comma y1. So simplifying this expression and substituting the values of x1 and y1, we get y1 of 1 as 1.167. Okay, now we'll apply the second iteration. Second iteration will give us y of y of y1 of 2. So for this again, if you observe carefully, the entire expression of y1 of 2 is same as y1 of 1. The only difference is in the place of y1 of 0, we'll be using this value y1 of 1, which is 1.1671. So we get y1 of 2 as 1.1675. Okay, so we'll apply the third iteration now, because it is was mentioned in the problem that we need to apply the iteration thrice in both the stage, in each stage. So third iteration will give us y1 of 3, which is 1.1676. It's almost same. So the final answer for y of 0.2 will be 1.1676. Okay, now you can try out these questions for practice. Modified Euler's formula, calculate y of 0.2, correct to 4 decimal place. By solving the equation, dy by dx is equal to x minus y square, where y of 0 is 1, and by taking x is equal to 0.1. Okay, it is exactly same as the problem what we have discussed. For your reference, I'll give you the answer for this problem, which you can verify. So this is the answer. Okay, thank you.